So a long time ago, there's a story about Isaac Newton sitting under a tree with an apple, falling and hit him on the head. Okay, but generally this story is considered to be false, although from everything I've heard, he was the kind of person that liked those sort of stories, and so even though that it wasn't true, when the rumor started, he didn't try to stop it. He definitely encouraged that rumor. So, but really, his biggest kind of contribution comes like this. Okay, let's pretend that let's go like this. Okay, so let's think of a cannon. All right, so if you fire a cannon off of like a cliff, okay, it's gonna fire. Eventually, it's gonna come down and hit the ground. Okay, well, if you fire it faster, it's gonna go further. Okay, if you fire it even faster, as it goes further and further, the Earth is even going to start to curve away from it. Okay? And he thought that maybe if you fired the cannon fast enough, it'd be so fast that the cannonball would fall all the way around the Earth. Okay? And so this concept is called Newton's cannon. And essentially, everything that orbits is following this principle. It's moving so fast that it falls around the Earth because it wants to continue in a straight line, but as it travels in that straight line, it gets pulled inward from gravity. And that same process happens again and again as it travels around the Earth. And this is actually how Newton first came up with his law of gravitation. Okay, he was thinking about the moon, and based on our knowledge of mass, the moon should just continue moving on in a straight line. But it doesn't. It orbits the Earth. Okay? And what he realized was that the reason it orbits the Earth is because the Earth is pulling on it and it's falling into the Earth. So the moon is falling towards the Earth, but it's moving so fast that as it falls to the Earth, it also moves to the side. And so by the time it's fallen this much, it's already moved that far that way. And now it's moving like this. And by the time it gets here, it's falling like that. And it's going to fall like that around the Earth. Okay? So let's think about if you're falling. If you're falling, you feel weightless. Okay? Because there's nothing pushing up on your feet. The feeling of weight that you get is from standing on something. And so this is why people who are in space orbiting the Earth feel weightless, because it's as if they're perpetually falling around the Earth. Okay? And so in his process of describing the moon's motion, what Newton realized was that the force that the moon experienced was proportional to the mass of the moon. And I don't know if this is how he came up with this law, actually. I know that that's the conversation he had, and that's how he came up with the concept of gravity. I don't know particularly how he came up with the law, but he knew that's proportional to the mass times another mass divided by the radius between them squared. Okay? And these would be the masses of two objects. So basically he's saying here that any two objects that have mass are going to pull on each other with a gravitational force. So that means that the Earth and the moon pull on each other with a mutual gravitational force. Okay? They're pulling equally strong on each other, and evidence for that we have on Earth is that the moon's pull on the tides, okay, causing us to have tides. And the sun pulled on the Earth, and the Earth pulls back on the sun. Now the sun doesn't really notice the Earth because the Earth has such a small mass, okay, which means it experiences a large acceleration based on that force. But the sun has very large mass, so it experiences almost no acceleration. Okay, so this can actually be, he brought this into an equation. Since all those things were proportional, he rewrote as an equation that was g times m1 times m2 over r squared. And then sometimes you're going to see it with this little r vector, and that's just saying it's in this direction, this kind of radial direction. We're just going to kind of ignore that though. Okay? But this value for g is called the gravitational constant, and it's something that can be measured. Okay? So in the background, I'm going to show you something basically that was developed by someone named Henry Cavendish called the Cavendish experiment, in which you can actually measure the value of g, okay, that gravitational constant. And so essentially what it is, you have right here in the middle this suspended styrofoam beam, and initially, of course, it wasn't styrofoam, but I think they use styrofoam because it's light, has little mass, and they have these masses on the ends, okay, and it's just hanging there, okay. And what's going to happen is they're going to put these masses on the sides, and due to the attraction between these masses and between these masses, it's going to cause it to rotate. And the force that's pulling here is that gravitational force of attraction between these sets of masses, okay? And then you're going to see them move those masses to the other side, which will cause it to rotate the other way. Okay, and this is called the Cavendish experiment, and it's evidence of an example of how masses attract through a gravitational force. And so it's pretty cool to see, and it's kind of crazy to think about, because when we experience gravity, it seems like such a strong force, but the reason the Earth's gravity is so strong is because it has so much mass. And so here you can see with things that have very small mass, there's a very small force, but that force does exist. So this value for g is 6 points, that the experimental value that's been measured is 6.67 times 10 to the negative 11th, and the units are newtons times meters squared per kilogram squared. And these are going to allow us to convert these meters down here and these kilograms here into newtons. Okay? And so the significant thing is this is a very, very, very tiny number. And gravity is actually a very weak force. Okay? As I mentioned before, the reason that we experience such a strong pull from Earth's gravity is because it has a very large m, okay, allowing for a very large force, okay, overcoming this very small, very, very tiny constant g. Okay, the second thing I want to mention is this, the r squared. That's also significant. Okay, gravity is something that is called a field force. So if you can imagine lines of gravitational force pointing inward towards the Earth from every point, okay, and it makes sense that they would be pointing inward because no matter where you are around the Earth, there's gravity pulling in. So no matter where you stand around this Earth, there's gravitational field pulling you inward towards the Earth. Okay? Now, if you think about all of the, if you were to kind of take Earth and capture it in like a balloon, okay, you would be capturing all of the gravitational field within that balloon, and you could, I guess, feel the gravitational field strength at every point along the balloon. Okay? Well, if you were to inflate that balloon and kind of double its radius, what you're going to find is that this gravitational field is spread more thin. Okay? Which means there's not as much gravity to go around the further away you get. They're spaced out further. Okay? And so we can quantify this by dividing by r squared, and this is called an inverse square law, in that for every time you double your distance, so if your distance goes from r to 2r, you're going to decrease the magnitude of the force by 4, okay, because 2r, if you square it, becomes, if you're dividing by it, instead of becoming 1/2, it's becoming 1/4. Okay, and we'll get some more examples of this later, but this is an example of something called the inverse square law, which applies to all things that are field forces. Okay, our first one here is this gravitational force. Well, there's other field forces besides this. We can think of magnetism, we can think of static force from electricity. Okay, we won't get into those at all this semester, but those are other kinds of forces, and even when you think about nuclear forces, they're all governed by this inverse square law.